This video provides an overview of the Doppler effect, both conceptually, but also the mathematics behind it. You will not be asked on our summative test when we have it to calculate things with the Doppler effect. However, for the practice worksheet, it is helpful to see the equation and see how what you hear might not match up with what's being given off by the source of a sound. The Doppler effect will also come up when we study light and when we talk about astronomy in quarter 4. The Doppler effect is defined as the apparent change in frequency, so the note that you hear, the sound that you hear, due to the motion of either the source, so the source being what actually makes the sound, or the receiver, who or what hears the sound. So again, the source is what makes the sound, and the receiver is who hears the sound. Now, if we think back to our facts that we know about sound, remember the speed of sound in a given medium at a specific temperature is going to be constant. And so if the speed of sound is constant, then let's look here at this image. If we think back to our wave speed equation, the speed of sound will equal the frequency of that sound times the wavelength of that sound wave. So in this picture, you can see here, these waves are farther apart. The wavelength here is bigger, and the bigger the wavelength, the lower or smaller the frequency will be in order to keep the speed of sound the same. Remember, frequency and wavelength are inversely proportional. So on this side of the picture with the policeman driving towards the person, we see that these waves are close together, so a short wavelength, a small wavelength, will then result in a high frequency, a larger frequency, to keep that speed of sound constant. So as you can see here, we have our source of our sound emitting waves at the same frequency, but due to the motion of the source of the sound, these wavelengths end up getting much closer together, and the wavelengths behind are further apart. And that is the Doppler effect. So again, close together, short wavelength, high frequency. Larger wavelengths, they're more spread out. Lower frequency, lower note that you hear. Mathematically, this is how we calculate the Doppler effect, how much the frequency appears to change for something we see or hear. So this prime, this little like apostrophe up here, this right here is the frequency that we actually hear or see as a result of the Doppler effect, as a result of either us moving or the thing making the sound or emitting light waves moving. This right here, this frequency with the little 0, is the actual frequency given off by the source. So if like nothing is moving, then you would end up with the frequency you hear is the frequency given off by the source. Because if this is 0 and this is 0, if nothing is moving, then the speed of sound divided by itself would be 1, which would leave you with frequency equals frequency. Now, V is for velocity, and then I've written out the words, so sound, observer, and source. So remember, sound is going to be the speed of sound. Observer would be how fast the person listening, so in this case, like usually it's you, are moving. And then finally, the source would be like the thing making the sound or giving off a light wave. So again, this is our equation for the Doppler effect. And notice how in the top we have a plus sign, and in the bottom we have a minus sign. Now that becomes important because velocity is a vector. That means that it has magnitude and direction. And so therefore, the velocity of the observer should be given a positive sign if the observer is moving toward the source. So if it's moving towards, the velocity should always be given a plus sign. If it's moving away, you should give the velocity a minus sign, a negative sign. So again, if the observer is moving toward the source, make that velocity value positive. If they're moving away from the source, then their value should be negative. So you could end up with a minus sign in the top if the observer is moving away from the source of the sound, because this value would be negative. And when you add a negative, it's the same thing as subtracting. Now, when you have the source doing the moving, again, same deal. If the source is moving towards the observer, make it positive. If the source is moving away from the observer, make it negative. So again, flipping back to our equation, if the source is moving away from you, you might have two negatives here. And remember, two negatives cancel and become a positive value. So again, the sign for the velocity of the observer and the source can change what you get inside these brackets that you're going to then multiply by the actual frequency to determine what frequency you would hear or see as a result of the Doppler effect. So some example problems for using that Doppler effect equation from our notes. If you look at your note sheet number 8 and number 9, that will be available in a separate video that will be posted within the next day or two. If you want to check out this video clip that's posted in Classroom, this right here is from The Big Bang Theory, and it shows Sheldon dressing as the Doppler effect for Halloween, and it gives a pretty good definition and then examples of what the Doppler effect is, how you would see it, and so I would definitely check it out because it will definitely help you remember what the Doppler effect is and how it works. As always, please email me if you have any questions about the content in this video, and I'll do my best to answer those between now and when we're back in class.